Okay, today we're going to talk about ionization energy and electron affinity. Both of these properties refer to the atom's attraction for electrons. They're going to be critically important concepts in determining whether something's a metal, nonmetal, or metalloid, determining chemical reactivity or stability. So these properties really determine the behavior of the element. Um, these properties are also driven by things we talked about earlier, and that is effective nuclear force and atomic radius. So it's important that you understand those previous periodic trends so that you can understand these periodic trends. And these periodic trends are the ones that really drive the behavior of the atoms. Now, before I get into the PowerPoint itself, I didn't actually start it as a slideshow. I want to draw a little picture for you, or a little diagram anyway, what ionization energy is. So I'm going to go to Paint here and use my finger to draw on the screen with my beautiful handwriting. Energy is going up the side of the page here. So that's E. You'll recall energy states are quantized. So there's level 1, level 2, level 3, 4, 5, 6. They get closer and closer together as you go up. We saw that last chapter. Remember also, these energy values are negative. And by the way, you notice I'm just using Bohr model here. Yes, each of these levels had sublevels and orbitals and blah, blah. Doesn't really matter for this discussion. These energy values are all negative. Right up here somewhere is an energy of 0 joules. That's 0 joules, not orange juice. So energy level 1 has energy of negative, I lost my cursor. That's all right. Has energy of negative something times 10 to the minus 18th. Energy level 2 is still negative, and so on. So if you keep going up closer and closer, eventually you'll get to level infinity. And at level infinity, I think we actually calculated this one day when I was out in the sub, gave you a worksheet. At level infinity, the energy is 0 joules. Now, if I take an electron, let's say for the hydrogen atom in its ground state, level 1, I can give it enough energy to jump up to level 2. We talked about this. It absorbs energy, usually a photon of light, to get there. If I want to go to higher energy states, it takes more energy, and so on and so on. What if I want to go from level 1 to level infinity? Well, the difference there is just the ground state energy minus the 0 joules. So it's just the ground state energy as a positive value. At 0 joules of energy, the electron is no longer bound to the atom. It has no energy anymore, so it's free to fly away wherever it wants. In other words, it's now a free electron. It has escaped the atom. Now that it escaped the atom lost an electron, so it's an ion. So the energy to do this, the energy to take the electron and let it escape the atom, is called ionization energy, because you've ionized the atom. So now that you've seen my beautiful artwork, we can come back to the PowerPoint, and I can actually start the show. Notice here in my little cutesy picture I put in, there's ionization energy coming in and the electron goes flying off. They show it flying off as a wave. Duality is a wonderful thing, isn't it? So, ionization energy is the energy needed to remove an electron from the atom in its ground state. We just got done talking about that. Each atom is going to require a certain number of joules of energy, and notice it's like 10 to the minus 18th joules or something like that. So because they're such small numbers, often what we'll do to measure them in the lab, and obviously it's not the kind of thing you do in a high school lab, but in general, to measure these in a lab, you would take a mole of atoms in the vapor state and then ionize them all at once and look at how many kilojoules of energy it takes to do it. Because now that you have a mole of atoms, it's enough that you get thousands of joules of energy used to do this. And so ionization energy is generally expressed in the unit kilojoules per mole. How many kilojoules of energy it took to ionize 1 mole, to remove 1 mole of electrons from the atoms. It's this concept of ionization energy is a measure of how tightly the electrons are held. If an atom is really holding onto its electrons tightly, maybe it has a very large Z effective, then there's going to be a very large ionization energy. It's going to take you a lot to rip those electrons free. On the other hand, if an atom is holding its electrons very loosely, has very low Z effective, it's not going to take much energy at all to rip an electron out of its orbital. I look at it like being a bully, which I am, of course. Someone's walking down the hallway with their books straight out at the end of their arms, one book in each hand. Well, some bully's going to come along and slap that out of their hand, and it's easy to do. Didn't take very much energy to remove those very loosely held books, electrons. If someone's a little smarter, is holding their books tight to their chest, if the bully wants to try to knock the books out of their hand, it's going to take a lot more energy to do it. You're holding onto your electrons more tightly, takes more energy to remove them. So notice, by the way, the factors involved there are how close they are to the nucleus or atomic radius, how close the books were held to your body, and also the Z effective, how strong your hands are in holding onto the books. So, I'll just show these last few things here. On your periodic table down here, as you go to the right across a period, the atomic radius is staying roughly the same. It's shrinking a little bit. Why is it shrinking a little bit? Because increased Z effective. Remember, you're adding protons to the nucleus, but you're staying in the same shell. And so you're getting more and more effective nuclear force as you go across. That's holding those electrons more and more tightly, and so it's going to take you more energy if you want to remove them. So as you go across a row, ionization energy gets larger and larger. Over here on the right, with your noble gases, is where you have the highest ionization energy, which kind of makes sense. You're going to have a hard time ripping electrons out of a noble gas. They want to hold on to them. As you go down a group, at that point, the major driving factor here is you're going to bigger and bigger shells. And so your electrons are further and further from the nucleus, which means they're more loosely held. They're feeling less force because the distance, the force drops off with distance. And so the electrons are going to be very loosely held down at the bottom of the periodic table as you go down the column. And so the ionization energy will decrease. It will take you less energy to rip electrons out of an atom at the bottom of the periodic table. So the atoms way down here at the bottom are very easy to ionize, to rip electrons free. The ones at the top are harder. So notice the trend here goes exactly opposite of atomic radius. You go across a row, the radius is shrinking, ionization energy is growing. For the exact same reason, increased nuclear force, pulling the electrons in closer, smaller radius, holding them more tightly, increased ionization energy. As you go down a column, atomic radius is increasing and ionization energy is decreasing, again for the same reason. You go down a column, bigger shells, less nuclear force, bigger size, less energy needed to remove the electrons. So once again, on tonight's worksheet, I'm going to give you like some atoms and say who's got higher ionization energy, who's got lower ionization energy. Now, there's a graph of again, atoms going from element number 1, hydrogen here, there was no element 0 obviously, all the way across to element 100 and something, showing the ionization energy values in kilojoules per mole. Now, notice hydrogen's right here in the middle of the road. You go across the row to helium and look how much bigger it is. Now you go to lithium, and then across its row to neon, it's increasing. Now to sodium, across its row to argon, it's increasing. Notice the noble gases, helium, neon, argon, krypton, xenon, they're shrinking as you go. As you go down the column, ionization energy is decreasing. As you go across this row, it's increasing. Across this row, it's increasing. Across this row, it's increasing. There's your transition metals doing weird stuff again, right? Now, something I wanted to mention here, these anomalies. Let's look at the second period. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Notice beryllium is a bit of a spike there. It's higher than it should be. And so is nitrogen. What are they doing? Well, remember, beryllium ends as an S2, full subshell. That full subshell has stability greater than you would expect otherwise. And so trying to rip an electron out of that stable full subshell is going to take you more energy than it otherwise would have. So you get a little spike there. What about nitrogen here? That's your P3, half full subshell. And so once again, you got a spike of ionization energy because it's going to hold those electrons more tightly than it normally would have given any other considerations. And so to break into that stable half-full P3, you're going to have to use more energy than you would have otherwise expected. This is our evidence of that half-full shell stability that we talked about earlier. If it weren't for that Hund's rule stability, nitrogen would be right here where the cursor is, right in between the rest of the row. Notice in the next period, the same thing happens with magnesium and phosphorus right there. You get those little spikes. In the transition metals, you get the little spikes spread out because you got the rearranging giving you 2 different D5s and 2 different D10s. So things get a little weird there. We won't even talk about lanthanides and actinides because they're just annoying. But that's ionization energy. And you see how the trends kind of make sense. Even the anomalies that we see in the graph make sense, which is kind of cool. Now, I got about 4 minutes left here, so I'm going to hurry through. That's first ionization energy, removing the first electron. What if you want to remove more electrons? Okay, well, it's going to take more energy. The second electron is harder to remove than the first. The third is harder, and the fourth is harder, and so on and so on. Because as you remove electrons, they get pulled more closely to the nucleus because there's less electron repulsion forces. Now, interesting effect occurs that you see down here. We're looking at multiple ionization energies of boron. So here's the energy, the first, the second, the third, the fourth, the fifth electron I'm removing. You'll notice the first ionization energy is fairly low. It doesn't take much energy to remove it. Second ionization energy is higher. It took more energy. That makes sense. Third ionization energy is higher. Makes sense. Fourth ionization energy just skyrockets. And then fifth is way up there again. Why is there this huge jump for fourth ionization energy? Well, look at boron's configuration. 1s2, 2s2, 2p1. First ionization energy, I removed the p1. The second, I removed one of those s's. We're still in level 2, same distance from the nucleus. The third, I removed my last s electron, so all of level 2 is gone now. I've got a full helium core. Fourth ionization energy, I'm going to have to break into that helium core. And boron says, no way, I'm not giving up that core, not without a fight. It takes a lot of energy. So that's why boron forms a 3+ charge. Because to form a 4+ takes ridiculous energy. Why does it take ridiculous energy? You're breaking into a lower shell. So once again, we're getting the same results we saw before. Each column, if you look at it, will give you the charge that you expect. But now we can look at it based on ionization energy. Okay, last topic is electron affinity. Ionization energy is talking about removing electrons. Electron affinity also measures attraction for electrons, but it's going to measure it by gaining electrons. So I'm going to take an atom and I'm going to hand it an electron and say, here, take this, and look at whether it gives energy back or I have to force it in there or something like that. So electron affinity measures attraction for electrons by how well the atom accepts electrons. It's also measured in kilojoules per mole. By the way, I'm not going to show you the graph for this because it's very difficult to empirically measure, and the graphs are kind of chaotic, so it's not going to really show you much. But it's going to follow the same trends as ionization energy. Increase across, decrease down. Why? Because it's measuring the same thing, attraction for electrons. Notice in both cases, francium down here is the smallest value of them all. It's got the smallest attraction because it's the biggest atom with weakest force. Fluorine over here, ignoring the noble gases, is going to have the highest of them all. It's got the strongest attraction. Strong is the effective smallest atom. So that means francium, very weak attraction, low electron affinity, it's not going to gain. Low ionization energy, it is going to lose electrons. Fluorine over here, high electron affinity, it's going to gain them well. High ionization energy, it's not going to lose them well. Okay, that's it for this. Next time we'll go into how this all fits together. But for tonight, we'll have a worksheet on this, and then we'll take it from there. And we're done for the day.